In a tiny structure beyond the reach of the human eye lies a society of particles. These particles function as we do in their everyday lives. They live in their homes that they call atoms. They belong to a stable family nucleus. They have their own character traits expressed in protons, neutrons, and electrons. They have jobs, resides in cities, and entertainment. And oddly enough, they have podcasts just like we do.
Live from Adamwood, California, it's Nuclear Nights, your source of nightly nuclear entertainment news. I'm your particle host, Nucleya Newton. Tonight we'll be interviewing celebrities, hosting our nightly trivia, and discussing the latest pop culture news. Now, our first guest went from being three little orphan particles to celebrities. They're the three members of Radiation, the newest band everybody's talking about. Please join me in welcoming our guests, Alpha, Beta, and Gamma! Thanks for inviting us. I'm Alpha.
Hi, I'm Beta, and I'm ready to discuss our radioactivity. Hey guys, it's your girl, Gamma. I'm so excited to be here, totally. Nothing can stop me from entering your show. Well, except for several inches of lead or a feet of concrete, but that doesn't count.
She's so ahead of it she can just penetrate through anything.
Alpha and I are more grounded. A sheet of aluminum can stop me, and paper and human skin stops Alpha.
Wow, I'm excited for you three main types of radiation to be here. So Alpha, you went from humble beginnings to becoming one of the biggest names in Adamwood. Yeah, Beta, Gamma, and I all came from unstable foster family nuclei. We're separated at birth, bouncing around from foster family to foster family.
So in every atom home, the family nucleus is involved in the decay. With an incorrect ratio of protons to neutrons, the nucleus becomes unstable. It has to be 1 proton to every 1.5 neutrons and not a subatomic particle more. The ratio also can't be less than 1 proton to 1 neutron, because then it becomes radioactive. Usually, large family nuclei, or those with more protons than bismuth, are unstable.
I heard those family nuclei just slowly decay, losing particle members. Definitely. My last foster home was a uranium-238. There were 92 protons and 146 neutrons. We used to be a tight-knit family of uranium-238, but we started fighting a lot. So I went my own way and my family went theirs. They became a thorium-234, with a nucleus of 90 protons and 144 neutrons. Just one step closer to stability.
Alpha here is amazing. She's nearly like a helium family nucleus with 2 protons and 2 neutrons. You can sum up her life in one equation. U-238 with 92 protons, an arrow pointing to TH-234 with 90 protons, plus He4 with 2 protons. U-238 shows what her family originally was, and the arrow is a yield sign for when her family split up. The number of protons and the mass must equal or balance on both sides of the arrow. You can use this type of equation for all decays.
That's amazing. Now, Beta, I heard your family life was similar.
Yes, my first family nuclei was an unstable lead-210 with 82 protons. I was discharged as an electron. Our family nucleus became a bismuth-210, as one of the neutrons was turned into a proton. The family nucleus' new positivity brought some stability back, but my second foster family was tough too. Coincidentally, it was bismuth-210.
So 83 protons and 127 neutrons? That's about the 1 to 1.5 proton ratio.
Oh my god, I was there too. Yeah, our family split into polonium-84, and I left. To reach more stability, our family nucleus just needed to get rid of our jittery energy, so Gamma was discharged as well. Totally, I don't leave without one of my particle sisters, ever. Gamma's crazy, she's just pure unaltered energy. But I'm, so glad that I'm not the same as Beta. She's, so tiny, and sometimes she's just like an electron, so negative, Other times she's small with a positive charge, like a positron. She just leaves, making her proton turn into a neutron, but, she never changes the mass of her family nucleus.
Wow, well, I'm really sorry, girls. It seems like you had tough childhoods.
Not at all. Radioactivity is natural. It's a part of life. It just makes our family nuclei, all the more stable. Well, it's just radioactive decay, which is the act of a nucleus spontaneously breaking down. That's right, and that's, why we decided to name our band, Radiation.
It's been a pleasure having you all here. Next up, we have our entertainment trivia right after these messages. Hi, I'm Tycho Churning, world-famous football-playing particle. As a child, I worked on a poor farm with my family. My life used to be tough as a child, but that was until nuclear tech changed my life. Nuclear technology gave us so many benefits, like lower greenhouse gas emissions from the agriculture, the ability to track fertilizers and pests, an increase in genetic variability of plants, and an increase in food production. My family finally had the financial stability it needed. Nuclear technology can help detect and cure diseases through radiation therapy, analyze pollutants, detect smoke in homes with alpha particles, and power beacons and satellites.
Before using nuclear technology, be aware of the impacts. Side effects may include destruction with nuclear weapons and reactor explosions, large amounts of nuclear waste, high expenses, high amounts of radiation, and non-renewable scarcities.
So come on, try nuclear technology today. Welcome back, I'm Nucleya Newton, and it's time for some entertainment trivia. We ask 4 questions and pick one random caller for each question from across the atomic nation. Here with me is our first caller, Thomas Tesla from Fusionville. Ready to play for $500, Thomas?
As ready as I'll ever be.
Thomas, nuclear technology is the latest craze today. Tycho Churning, a football-playing particle, raved about it. Tell me, what is the scientific definition of nuclear technology? What are the different types?
Nuclear technology is basically a collection of methods and inventions that uses energy released from fission of certain elements as atoms split. The different types include carbon dating, which is used in paleontology to find the age of rocks, and then chemoradiation, which is used in cancer treatment, sterile insect technique for pest control, nuclear reactors, which can generate electricity, imaging, which creates pictures with X-rays, and food preservation. Scientists hope that one day nuclear tech will be possible through viable fusion techniques.
Looks like Thomas is going home with $5,000. Now, our second caller is Carl Kepler from the Neutral Lands. Now, Carl, earlier this week, Bill Rohr complained that his house was in wild disarray. He said that his electrons were way too excited. Explain how electrons should be positioned.
Nuclei, electrons in our atom homes follow an electron configuration. In neutral atoms, the number of protons equal the number of electrons, while with a Bohr model, electrons are located in rings of the electron cloud. The lower rings fill up first, and there are sublevels, S, P, D, and F. Chemical properties of an atom home can be determined by valence electrons, or electrons at the outermost ring. Following the octet rule, atoms with 8 valence electrons are typically stable and don't react. Atoms with 1 or 7 valence electrons are highly reactive.
Pack your bags, Carl, because you're getting a pair of concert tickets to see the band Radiation.
Thank you so much.
No problem. Our next caller is Charles Copernicus from Isopolis. Charles, famous twin actresses Florence and Frances Frank live in atom houses that are isotopes of each other. What does this mean?
I think that it means that they have the same number of protons, but a different number of electrons?
Not quite. Those are ions. Isotopes are atoms with the same number of protons and same element, but a different number of neutrons. This gives them different masses, but similar chemical properties. They're expressed through isotopic notation, which is typically the named other element connected to their mass with a dash. The average atomic mass of an element is calculated by multiplying each isotope's mass by its abundance, and adding these products together. Isotopes with the most abundance play the biggest role in the average atomic mass. Now, our final caller, Daniel Dalton from Nucleago. Now, Daniel, singer Rachel Rutherford controversially said that she hated subatomic particles. What are the 3 main subatomic particles and where are they found? Protons, neutrons, and electrons are the 3 types. Protons have a positive charge, electrons have a negative charge, and neutrons are neutral without a charge. In an atom home, the protons and neutrons are in the family nucleus. Both are 1 atomic mass unit. The electrons are all the negative charges surrounding the nucleus in a large electron cloud. The electrons are tiny. They have a small mass of 1,836 AMU. Protons determine what type of element an atom house is. Well said, Daniel. Your grand prize includes $200 plus tickets to the Radiation concert. Now, thank you all for tuning in to Entertainment Trivia. Keep listening as Atomwood Gossip begins.
Hi guys, I'm Carrie Carson, your nightly gossip analyst. It's been a real whirlwind in Atomwood.
Oh, I bet it is.
So Nuclea, the rumor mill says that famous actress Ada Proton is facing marital issues. Her family is decaying like crazy.
But that's crazy. Didn't she just get married a couple of days ago?
That's right, Nuclea. Ada's family nuclei was just unstable and radioactive. As you know, Ada is married to Benjamin Pitt, and they adopted 14 little particle kids. Their family nucleus is like a californium-253 with 98 positive protons and 155 neutral neutrons.
So her family nucleus is so unstable that it's just decaying now?
That's right. The atomic entertainment industry calls the amount of time it takes for half a family nucleus to decay a half-life. At the rate Ada's going, her californium-253 isotope has a half-life of 17.8 days.
That fast?
Well, we know that Benjamin gradually left with 7 kids in 17.8 days. Now only half of the californium-253 nucleus is left. Analysts say that after another 17.8 days, 4 of the particle kids will leave, and there will only be a quarter of the family nucleus left, and so on.
That's so fast. So in less than 2 months, Ada's family nucleus would just be 1/8 of its original size? All she'll be left with is 1 child.
That's right, Nuclea. This could be modeled by our special half-life equations. Basically, you take the amount of time that passed and divide that by the half-life. You then raise the number 1/2 to the power of the answer you just received, and you multiply that by the mass of the sample. That's how you determine how much of a family nuclei is left. Those radioactive isotope samples just get smaller and smaller over time, releasing particles.
Wow!
Half-lives are used for determining the exposure in a film, carbon dating, and even financial calculations. Now, Ada claims that this wasn't just any radioactive decay. Normally, californium-253 decays by itself in natural radioactive decay. An unstable family nucleus just naturally releases particles and energy, decomposing until it reaches stability. However, in a statement released today, Ada says that outside particles disrupted her family nucleus. She says that a slow neutron paparazzi bombarded into her family nucleus, making it overly unstable.
So it's induced radioactivity then?
Exactly, but induced radioactivity is often to a stable nucleus. Californium-253 is just naturally unstable, and radioactivity was bound to occur anyway.
Poor Ada. You know, Curie, it seems that marital issues and radioactive family decay is everywhere nowadays. I hear that an unhealthy amount of radiation just leads to health issues.
Nuclea, you have nothing to worry about. Particles like you aren't really exposed to that much radiation. Certain factors like X-rays, plane rides, elevation, and radiation therapy increase your radiation dosage. But on average, those of us in California only get 200 to 300 milligrams a year. In Acromanta, that number is 300 millirems, and for the average American, it's 600 millirems. Experts say that adults like us are fine if we have less than 5,000 millirems of radiation exposure a year. Minors shouldn't have any more than 500.
That's good news, Curie.
Well, I have some more good news, Nuclea. Adam Wood's favorite particle couple, Hawk Hubble and Dorothy Darwin, just tied the knot yesterday through fusion.
Oh wow. Now, I hear that you got to attend their wedding ceremony?
Yes, I did. It was a lovely ceremony. Hawk and Dorothy came together, forming a larger family of nuclei. Hawk is a helium-1 particle, just one positive proton. Dorothy, on the other hand, is hydrogen-3, or tritium. Her nucleus is just one positive proton and two neutral neutrons. And when they combined, you could just feel this amazing energy being released, you know?
I bet. That's just what stars do, don't they? Thank you, Curie. Now, Nuclear Nights is made possible with these sponsored messages.
Are you feeling lonely? Try Bond.com, where you can find your perfect match. You'll release so much energy, it will be amazing. Visit our website or call 1-800-BOND today. Be a part of nuclear fusion and join together with another atom. After all, fusion created virtually every element heavier than helium. Bond.com, fusing the future of together.
Are you feeling like your bond just doesn't work? Get nuclear fission counseling at break.org or call 1-800-FLEE-TODAY. We can bombard your nucleus to make the split. Break apart your atom today.
As the evening draws to a close, I'd like to give you my nightly recap. Radioactive. Unstable family nuclei like those of added protons decay. This is due to an unstable ratio of protons and neutrons in the nuclei. A half-life is the amount of time it takes for half a sample to decay. There are three types of radiation. Alpha, who's like a helium nucleus and large. Beta, who is a fast electron or positron. And gamma, who's pure energy. Balanced equations can be written to show radioactivity as unstable nuclei begins to decay and split. Proton quantities determine elements. Isotopes have the same number of protons but a different number of neutrons, showing which forms of nuclei are stable. Natural radioactive decay results from unstable elements, while induced occurs with stable nuclei and particle bombardment. As a society, we aren't exposed to dangerous amounts of radiation, although different factors account for different amounts. The world of nuclear technology provides hope for the future. We've made great progress in taking advantage of reactions of the nucleus to produce nuclear technology. From saving cancer patient lives with radiation therapy, to generating electricity for cities, to destroying populations with weapons, nuclear technology has impacted the world greatly. We live in a world with no limits on what we can do. I'm Nuclea Newton, and I hope to see you next time.